Okay, this is lesson 4 of unit 1. We're talking about number systems. The one big number system we're going to talk about is the real number system. This one is the largest that we're going to look at this year. So that guy is the largest number system that we're going to look at. So from lesson 3, we talked about rational and irrational numbers. So decimals that end or repeat are rationals, and they can also rationals because they can be put into a fraction. So that's also super important to know about that. So they can be converted into fractions, whereas the irrationals cannot be put into fractions. That's the biggest difference. Also, irrational numbers, this is where we're going to get our non-perfect square roots, and there's many, many more of those. So these guys, irrational numbers, we're going to write our examples down coming along. So it says the set of rationals and irrationals are under the umbrella of the real number system. So if the real number system were a diagram, which we're going to draw in a moment, and we're going to see it, it's on the bottom actually, a diagram, it's going to tell us what that actually means. So let's talk about our smallest set. So this is number 1. This is our smallest set. The smallest set of numbers. It's also known as our counting numbers. We don't start counting at 0. We start counting at 1. So these are our whole numbers. There are no fractions, no decimals, no negatives. Okay, so in this system, there are no fractions, no decimals. Okay, so no fractions, no decimals, and no negatives. The only thing that's different between the natural system and the whole number system is the whole numbers include one extra number, and that's the number 0. So these are considered as a definition. All natural numbers, oh my gosh, it is glitching hard here, hang on. Natural numbers and 0. So it's all natural numbers and 0. So now they're opening up the number line by one more number. The integers is our third set. The integers, there's more numbers in the integers because the integers open up the negative side of our number line. So our integers, these are positive and negative whole numbers. Okay, so positive and negative. In the first 3 sets, all 3 sets here, there are no fractions, no decimals, none. Okay, the first 3 sets, no fractions, no decimals. Okay, so no fractions and no decimals in the first 3 sets. However, we know from the previous lesson that our biggest 2 sets in the real number system, we have rationals and irrationals. So number 4 is rational numbers, and this is where it tells us that we can be writing them in fraction form. So A over B, it says where A and B are integers. That's what an I means. That funky letter E, this here, I'll show you, I'll highlight it for you. This in green here, that funky letter E, that is a symbol that means is an element of or is contained in. So that means in symbols that A and B are in the set of or contained in integers. So that means they can only be integer numbers, no fractions, no decimals, they can be positive or negative. That's what that A-B-E-I means. Okay, so it's symbolic. So it means they can be positive and negative integers. But then it tells us something specific about the B number on the bottom. You can never have your fraction have a 0 on the bottom. So that's what this is indicating. B cannot be 0. So all that means is the bottom of your fraction can't be 0. Okay? So that means the bottom of any fraction cannot be 0. Okay, so the bottom of any fraction cannot be 0. That's what that's telling us, that b can't be 0. Then we get irrational numbers. So with the rational numbers, we know we also get decimals. So we can get decimals and fractions, but on the other side, we don't get fractions. We only get decimals. Now let's differentiate the decimals. So if I talk about rational numbers, the kind of decimals I get, there's two kinds. I get the repeating or I get the terminating. Okay, so they're going to repeat or terminate. That's the kind of decimals you're going to see in rational numbers. If it's irrational numbers, you are going to see decimals that run on decimals, which means they are non-terminating. So that right there, non-terminating, is the run-on decimals. So what kinds of numbers are going to give us run-on decimals? These will always be the non-perfect square roots. So every non-perfect square root. So every non-perfect square root. Boy, I wish this would write nicer. So every non-perfect square root. So root 1, root 2, root 3, root 5, root 7, root 8. All of those are going to be run-on decimals every time. And what do we know about run-on decimals? We can never put them into fractions. Okay, so that's also the big thing here about rationals. You cannot put into fractions. Okay, so you cannot put them into fractions. That's what that's telling us. Boy, that looks like chicken scratch. That's terrible. I really wish this was working better. Can not be put into fractions. I tried. They can't be put into fractions. All right, now on the diagram below, we're actually going to write where these are, and we're going to put the symbols where they belong. So on the left-hand side, these are all the real numbers. The real number system gets the symbol R. So the symbol R is for the whole thing. So that means this entire thing is the real numbers. Okay, the entire thing. Now, just the left-hand side. So just this side way over here. Or it could have been on the right. Doesn't matter which side you draw it on. Those are going to be the irrationals. So these are Q with the line over it. These are our pi. Those are our non-perfect square roots, like square root 2. Okay, so pi, all the run-on decimals. That's going to be your irrational numbers. The rational numbers are found in the other side. So all of these are rational. Okay, so now this is where we're going to find our fractions and our terminating decimals and our repeating decimals. Okay, so fractions, repeating decimals, and terminating decimals. Now, the other smaller, as we go, we get smaller. So if we start from the very, very inside, the one that would be on the very inside would be n for natural numbers. That's our counting numbers. So that's going to be +1 all the way to positive infinity. So it goes on forever. So 1 through infinity. Then it shows us W for whole. So that's all of those natural numbers plus 0, the number 0. It includes 0 and all those natural numbers. That's why the whole number circle has the other one inside of it. And we're going to notice the other one is integer. This is our positive and negative numbers. But again, there's no fractions and no decimals. There's no fractions and decimals till you get to this outside layer. And that outside layer will give us our fractions and decimals. Okay, once you've got those written down, I'll get you to turn your page. All right, now what we're going to do is we're going to categorize the numbers. We're going to take a look at a few numbers and we're going to put them in the categories that they belong. Now, for example, if I had the number, if I want to categorize, let's say the number 4. Well, the number 4 is a whole number because it's 0 to positive infinity. It's also a natural number. So what you try to do is you try to find out which circle is the smallest that it would fit in. And then it's going to fit into every circle outside of it, except for the irrationals, okay? So number 4 is going to fit right where? He's going to fit into this. The 4 is going to fit into the naturals. Well, if he fits into the natural, that small one, that means he's also a whole number, he's also an integer, and he's also a rational. So the number 4 would categorize as natural, whole, integer, rational, and real. So it would be part of 5 number systems. Okay? Natural, whole, integer, rational, and real. There's only 6 systems. The only one it's not in is that irrationals where pi is. Okay? So it's not going to be over there. So that's how we would categorize where they belong. So now what we're going to do is we're going to turn the page and look at the examples it gives us. And then we're going to try and categorize where would they fit. So I can redraw the diagram real quick here. So we've got natural, then we would have whole, then we've got integer, then we've got rationals, that's our Q, and then we've got irrationals are just not part of those circles at all, okay? All right, so which part? And every single one of them is part of the real number system. So every single one of them is going to have the R as a symbol. But which other system do they fit in? Well, the number 9 is like the number 4. It's going to fit into the natural, the whole, the integer, the rational, and the real. So it's going to fit into 5 number systems. Now, a perfect numeric response question would be, categorize this question, and it might say, how many number systems does this number belong to? And you would have to label, the number 9 there would belong in 5 number systems, okay? 11 over 7, if it's a fraction, you need to solve it into a decimal to see what kind of decimal it gives you. But you also know if it's a fraction, it's a number that can be put in a fraction. Where do we find fractions only? There's only one spot we find fractions. One spot alone. Rational, good. So right around here, those are the fractions. So the fraction is always going to be a rational. So that's our biggest system. So he's going to be a Q, and then everyone is a real. So he's going to be a QR. So that guy fits into 2 number systems. And it's a fact that he's a fraction that he's going to fit into the outside one, that rational. All right, square root 5. What do we know about square root 5? He's non-perfect. Well, if he's a non-perfect, okay, so he's a non-perfect square. All non-perfect squares are in the irrationals. And then, of course, they're in the reals. Okay, because every number is part of the real number system. So he's irrational because non-perfect squares go in the irrational part. And then they're real. Now, -7. Where is the only spot that I can find negatives to start with? Integers, good. So if I say that -7 is going to be an integer, He's going to fit into the bigger circles around him. So what else would he fit into if he's an integer? Rational. And the last one everybody's in? Real. Okay, so that guy would be in 3 number systems. Now, what if you had a perfect square? So, for example, let's say we've got the number square root 25. Where would that guy belong? Now, for perfect squares, you have to solve them. Even non-perfect squares, you got to solve them. But if I solve this non-perfect square, it's going to be a run-on decimal. And we know that run-on decimals are all irrational. Okay? Whereas if I solve square root 25, I have to solve it. And when I solve it, it becomes the digit 5. So the digit 5 is going to be like the digit 9. It's going to fit into everything except for the irrationals. Okay, because only non-perfect squares or run-on decimals go there. Okay, so that's an example. So this guy here, he would fit into 5 systems. Okay, now it says, explain why 9 belongs to 5 systems and negative 9 only belongs to 3. How come? We're talking about on the number line right now. Jaden? Exactly, one's positive and one's negative. So on the number systems, I'm just going to show you on a number line. I'm going to draw a generic number line here. I'm going to put 0 in the middle, 1, negative 1. So from here on the number line over, those are natural numbers. From here on the number line over, those are whole numbers. The minute you show negatives and positives, you're everything on the number line. The only thing you are not is the fractions and decimals. So if you're an integer, you're all 3 of those. Okay? So these guys, if you look at the number line, it opens the number line. We're starting at 1, smallest set of numbers. Then we open up to 0, the next smallest set. Then we get a little bigger. We open up the negative side of our number line. So now we've got the negatives and the positives. The minute I start putting numbers in between those digits, so the minute I start saying that now I've got numbers in between these guys, those are my fractions and my decimals. So the minute I tell you you've got fractions and decimals in there, now we've hit the rational numbers. Okay, so rational numbers are the fractions and decimals. So these 2 would be the rationals. Okay, everything else, so this guy's integer, this guy's whole, this guy's natural. So if you need to see it on a number line to see where the number values are possible, that's how you could show it. Okay? All right, we're going to look at part B now real quick. There's only 3 parts to this lesson. Part B is now talking about square roots and perfect squares. All right, so it says all positive numbers have 2 square roots. We discovered that in our first lesson, that every square root has a possible negative answer and a possible positive answer, because you can get a negative times a negative to give you a positive answer. So because of that, you have a secondary root, which is your negative, and you've got your primary. Your primary of the positive is always the one you want. How do you know if you're looking for the negative one? The way you know you're looking for the negative one is if they show a negative in front of the sign. So let's take a look at the example they're showing us. So it says the square root of a perfect square are always rational. So it says the square root of 16 is 4 and negative 4. Because I could have 4 times 4 and negative 4 times negative 4. They'll all give me a positive. But when I show you a positive 16 under my root sign, it only wants the positive answer. The way you know it wants the negative answer is if they put a negative sign in front of the square root. So if it shows me this, if it shows negative root 16, Then it's telling me it wants the negative answer. Okay, so it's going to show you it wants the negative answer by putting a negative sign out front. Otherwise, it's always going to be talking about the positive. Okay, so you're going to get true and false questions. And one of the true false questions could say, okay, I could say to you, square root, let's just go with 9. Square root 9 equals plus and minus 3. True or false? Then I could say square root 9 equals only positive 3. True or false? Which ones of those are true? Only one of them is true. Which one is true? The first one or the second one? The second one. The only time we have to mentally understand that, yes, there's two answers. We have to mentally understand that. But we only ever want the positive one when they show us the positive underneath. The only time you want the negative is if they show the negative in front of the negative sign or the root sign. Okay, that's the only time they want it. So you're going to get those true-false questions. So we're going to see a list of our perfect squares over on the right-hand side. So what we're going to do when we try to estimate numbers is we want to try and see which numbers is it close to. In grade 9, we did benchmarking, you might remember. So that's kind of what we're doing. So 46. Now, if it's under the square root sign, you're looking on the right-hand side. So the right-hand side here, those are your perfect squares. Okay, those are the perfect squares. And on the left, those are the factors that make it. Okay, so what makes a perfect square of 100? 10 times 10. 10 would be the factor. 100 is the perfect square. So 46 is in between these two numbers. But who's he closer to? He's closer to 49. So the answer here is going to be between 6 and 7. And we know he's going to be closer to 7. So he's over halfway. So I'm going to roughly say I'm going to estimate 6.8. And now what we're going to do is we're going to check on our calculator. What is my answer if I check on the calculator? It's actually 6.8. So I did pretty good on that. But we could have just picked our general closest root. So I would have said my closest is 7. And 7 is close to what our real answer was, 6.8. So let's take a look at C right below it. Well, square root 5 is close to the number 4. And we know that the square root of 4 is 2. So that means this guy's answer has to be a little bit bigger than negative 2. And it wants the negative sign. So it wants the negative answer of it. So it's going to be close to negative 2, but a little bit bigger because 5 is bigger than 4. So it's going to be a little bit more. So if we actually type in square root 5 now and put a negative in front, we're going to get negative 2.2. It's a run-on decimal. That's why we're putting approximation, because we are rounding. Okay? So the actual answers, come on now. The actual answers, I'm just going to highlight here for you, the actual answers. But what we're doing is estimating how close they are. So let's look at B. B is a little bit crazy. So B's got a whole bunch of numbers everywhere. What do we know about a number sitting beside another number? What does it mean? Multiply. Good. So that means if a 2 is sitting beside a root sign, it means timesing. Same as that 5. It's timesing to the answer of that number. So root 18 is close to the number 16. So if I go square root 16, I'm going to get 4. So this is like taking 2 times 4, which gives me 8. I'm using big fat dots in between the numbers for multiplying instead of x's because we start solving for x's. Root 37 is close to root 36, which equals 6. So this is going to be 5 times 6, which is 30. So my answer is going to be close to, close to 38. And now if we type it in, you're going to type it in exactly as you see it. So you're going to go 2 square root 18 plus 5 square root 37. And I want to see what you get for an answer. Round it to 1 decimal place, please. And see what you get for an answer. And we will highlight our actual answer here. So what's our actual answer to that question? Same as this one, we'll put an actual answer. So who's got the actual answer for B? What would it become, do you think? We're really close. Our answer's really close. Yep. Yeah, and the 8 repeats, right? So it should be 38.9. So it's 38.9 roughly. Okay. So that's what it actually equals out to roughly. So our answer of 38 was fairly close. Where do we use estimation? Always when we're talking money. If you've only got a $100 bill in your pocket and you know you've got to buy a couple things, you're going to estimate the costs. If something costs $19, you're going to round it to 20. Okay, just in your brain to say, okay, I spent 20 bucks, I got 80 left. Okay, that kind of thing. All right, we have a double square root. Holy smokes. Now, which number is 95 close to? Is he closer to 100 or 81? 100, good. And what do we know the square root of 100 is? 10. So we're going to go square root 100, and then it becomes square root 10 underneath. So, because you're double rooting. So if I've got double root, this is what it would look like. If I've got double root 100, it behaves like a bracket. Root signs behave like brackets. So that's like having a bracket inside a bracket. So that means this part here in black is the part you solve first. Well, that's what we got as a 10. Okay, but it's still under that original pink root sign. Okay, it's still under 1 root sign. We haven't taken the root sign off. Now we take a look. What is the 10 close to on our list? 10 is close to 9. So this guy is close to root 9. So his answer should be close to 3. And now if we actually figure it out, if you put a double square root sign on 95, figure it out. See what you get for a decimal. We're close. 3.1. Yep. You should get 3.1 as the actual. So we're very close. So estimation can really help us out, especially when you're trying to think, if it's a multiple choice question and you're just estimating you can usually eliminate 2 of the answers. So then you've got a 50-50 shot of getting the question right. Okay? So estimation really will help you on quizzes. All right, turn your page. This section, that's a 20-1 section. We don't have to go through that. But we do need to talk about cube roots, because cube roots are pretty cool. So how are they different? They have a different number inside the check mark part. So in a square root sign, we have a hidden 2 there. Okay, that's the only time the digit 2 will ever hide. Otherwise, the only other digit that can hide ever is a 1. That's the only time a 2 can hide. Now, what does the 2 indicate? It means that one number was multiplied by itself twice. That's what that 2 tells me. That 2 factors multiplied to give me that number. Now, a 3 underneath is going to mean that 3 numbers multiplied to give me that answer. And it's 3 identical numbers. So here, 2 factors, and it's identical. I'm going to write identical up here. Oh, my goodness. Why, oh, why? I-D-E-N-T. Okay, identical factors. Whereas here, we're going to have 3 identical factors. Now, we know that with a perfect square, so with square roots, to get a square root, let's say if I have square root 25, we know there's 2 possibilities. The numbers must be identical in every way. So I'm going to get a 5 times 5 or a negative 5 times negative 5. Both are going to give me a positive answer. When you've got a cube root, all of your numbers are either all going to be positive or they're all going to be negative. And we know that with our negatives for a square root, the negatives stay outside. Okay, that's if it's a square root. But if it's a cube root, the negative can go underneath. And the reason it can is because 3 negatives will multiply and give you what kind of number? A negative. So that's why you can have a negative underneath the root sign. So cube root. Let's say if I've got, well, they've got negative 27. Let's go negative 64. That is specifically telling me that this number was negative 4 times negative 4 times negative 4. If it wanted the positive number, 4 times 4 times 4, it wouldn't show me the negative. In our square roots, if it wanted the negative answer, the negative would be sitting outside the root sign. Not in this case. If it wants the negative will be under with it. Okay? So the negative sign can go. Oh, hang on. Let's try this again. The negative sign can go under. Boy, it takes me 10 minutes to write that. Okay, so the negative sign is allowed to go under. Now, if you don't get a perfect cube, it'll be a run-on decimal. So here I've got the list of the perfect cubes. So what does 2 times 2 times 2 become? 8. 3 times 3 times 3 becomes 27. So again, the cube root of a perfect cube is going to be rational because you're going to get a terminating answer. However, if it's a non-perfect cube, you're going to get a run-on decimal, just like the non-perfect squares. You'll get run-on decimals. So now we're going to estimate these guys just by looking at where they belong over here. So if I look at the number 11, 11 is in between these numbers right there. Okay, 11 is closer to which number though? Well, he's closer to 8. So his answer will be closer to 2. So this guy is closer to 8. So the answer is closer to 2 than 3. And he's less than halfway because the next number is a 27 and 11 is very close to the 8. So we could say approximately 2.1, 2.2, 2.3 might be even too much. So if we actually figure the answer out though, what do we get for an answer? Now, if you don't remember what your math button or what your cube root sign is, if you want your cube root sign, you're going to hit math 4. So math 4 is your cube root sign. Okay, math button number 4. So now if I figure it out, we're going to get an actual answer of 2.2. So if we guessed approximately 2.1 and the actual answer is around 2.2, we did a reasonable guess. We did a reasonable job of estimating. So the actual answer, 2.2 when it's rounded, of course, because these will always be run on decimals. All right, last two. Let's look at B, cube root of 120. Well, 120 is in between these ones right there. So if 120 is in between 64 and 125, but he's really close to the 125. So that means his answer is going to be closer to 5 than it is to 4. So this guy is closer to 125. So his answer, I'm going to say estimate, I could say 4.7, 4.8, or 4.8, something like that we could estimate, and then we'll find the real answer and see what it is. So go cube root 120 and see what you get. What is it? 4.9? 4.9 rounded. Perfect. So the actual answer is quite close to what we got. All right, I'm going to put a little that guy there for our final real answer. Now, these ones, we got to figure these out separately. One is a cube root, one is a square root. So we have to do them separately. So square root, 70 is close to which number? 64 or 81? He's closer to 64. That's who he's closer to. And what's the square root of 64? 8. So this guy's answer is close to 4 times 8, which would give us a 32. Now we're going to do the guy on the right. The cube root is 70. 70 is close to 64. So if I said cube root 64, that means his answer is close to positive 4. So now I've got a negative 4 timesing by 4, and that's going to give me 16. So I've got 32, subtract 16 is going to give me roughly 16. That's our estimate. And now we're going to type it in. Type it in exactly as you see it and see what you get for an answer. Type it in exactly as you see. What are we getting for an actual answer on this one? Yep, what'd you get there? Yeah, 17.0. Perfect. So the rough answer that they got estimated is 17. Our estimate of 16, really close. That is the end of lesson 4. The next page, that's extension, that's all 20-1. So you don't need the absolute value on the next page. So that means this we do not do. This is 20-1. That's why it says extension. So we don't need that page. So that means you're going to omit those questions. You're not going to do 19 to 21. You're going to omit, which means don't do them because they are not part of our curriculum. They're just extension to 20-1. All right, that's the end of our lesson.